So before I get started, really quick question for everybody in the audience. How many robotic nerds do we have? Show of hands. Not everybody. Okay, maybe some salespeople came. So what I'm going to do.
Sales guys are actually nerds.
Nothing wrong with sales. I'm going to tell everybody 3 easy steps how to become a robotic nerd. Okay. Robotic engineer. Okay, there. So first step, you got to take that sticker. Second step, you got to put on your laptop. How many people have a sticker of a robot on their laptop? Hey, nice one. It could be a ROS-I, it could be your own sticker. That's step 2. Okay, so I'll got to tell a little bit of a story before I get to step 3. So what's interesting about a robotics engineer is there's a lot of focus here on software, right? Everyone's like software, software, software. What's interesting, in my opinion, is we're multidiscipline engineers. We're electronic engineers, we're mechanical engineers, and we're software engineers. And putting all that together, selling that to our company, that was tricky. So third step, you got to tell everybody you're a robotics engineer. You do that long enough, and then people just believe you. Is it moving? Oh, now I'm having technical difficulties. Nope. I don't have the whole presentation memorized. Escape. Try this one. Weird. Let's try now. No, I think it's because it's. Okay, that'll work. Okay. So Matt did a really good introduction. He told a little bit about me. What he didn't really touch on is I didn't start in robotics. I haven't really done robotics that much at all, actually. I've probably been out of school since 2005. It says right there, a computer engineering degree. Worked in the oil industry because they were the ones that took me. Learned a lot about oil and gas, learned a lot about controls, did a lot of software. Industry went to crap. Went over to a paper mill for a while. Worked in marine construction. And then in 2018, my boss called me and he said, hey, you want to work on robotics? Had no idea what robots were. It's not working again. What did you do to get out of it? Let's try this.
We're having all kinds of technical difficulties today.
Hopefully the video works.
Just run it.
Okay, that's fine. That's fine. So, again, really important here. We were a very small team of people. So, yeah, let me back up. This is my second sort of talk like this. So I'm doing a little bit of recap for some of the people that weren't here. I recognize some of you, but I'll do a really quick recap. But basically, we started with a really small team, right? We were really smart at mechanical. There were some of us that were really good at software, some of us really good at electrical, right? But we weren't robotics engineers. And I have to say this, I'm just going to throw this out. What I found was if you were a mechanical engineer first and then you learned ROS, you turned out to be a lot better. So to shout out to Michael there, he was our first robotics engineer, but he worked for Southwest Research. He taught us all how to be robotics engineers to some extent, right? So what did we do? We partnered with people like Southwest Research, Iskawa, and we just had to learn, right? So we took ROS courses. We went to San Antonio. Again, we relied on the community. All those conversations where everybody's talking and saying, hey, go to the Q&A, Google really helps, trust me. Finally, just a lot of long hours. A lot of people say that cliche term, fail fast and fail cheap. Well, my company likes to make money that I work for, so we had to succeed fast and succeed cheap. We didn't have the option of failing. So a lot of long hours trying to get stuff to work. So where did that get us? After about a year, a little bit more than a year, we had this, our first hands-free drill floor. It's not super impressive, I know, for a lot of people because it's a robot and it's going out, grabbing a pulp and going like this. But what this actually did for our industry was really important. This drill floor was full of people, right? It had 3 or 4 people on the drill floor just to move this piece of pipe safely, right? So ROS And on top of that, our proprietary control system, we were able to take all the people off the drill floor in a year. And then here's some of our legacy equipment, not as interesting, but basically it just screws in the pipe. I'll get to that a little bit. So, okay, right. Like I said, we moved pipe. So what? What's next, right? We're not done. So the overall control system, it wasn't complete, but we had a solid base to build on, right? We had a good framework in ROS. We leveraged a lot of the community. We knew how to plan past now. We were robotics engineers. Sorry, Michael. You could come visit for free. So what was the robot to us, right? We weren't building robots and we weren't doing a specific application to say, it's going to do this one thing, right? Which I think I see a lot of, right? Everybody's focused on certain applications and solving that one problem. But really for us, the robot it's a plug and play transport mechanism. We need it to do many jobs, right? So how do you do that? Well, one of our big constraints was you can't run anything through the robot, no utilities, no power, no sensors. So the robot needed to be swapped out. So this sort of gets the next step of our journey. Well, we made a twist claw, which I don't know if you saw, it just encapsulated the pipe, but we needed a way to take that twist claw off and put on other tools. So we've got the doping head, which we'll explain a little bit more, but it goes inside of the pipe and it sprays dope while it's coming out. We've got the stabbing guide, which sort of helps the pipe get stabbed in. Mud containment, which keeps mud from squirting everywhere. But the way that we did that, and that's why I've highlighted it bold, is it's a purely mechanical QD. And I think for our system, that's what makes it really unique. There's no air, there's no hydraulics, nothing goes through it. We use the robot in this rack right here, which is this guy, to come in and disconnect, which we'll show a little bit in a second. So basically this actually wasn't that long ago. This was probably 3 or 4 months ago. Through our top level control system and all the way down to ROS, we have two things that we did. We have a teach mode, and then we have this quick disconnect functionality. So nobody has to go outside and change tools. They just say, okay, I'm a doper head. Now I'm a mud bucket, right? And you just press a button. The teach functionality, which is really interesting, if you knew the details of the QD, it's very accurate, right? So you can sit there with a pendant, right? Like a Yaskawa pendant, and put it in the rack and you're standing there and you can save that trajectory, but okay, now it's on the pendant. How do we get it into ROS? So you turn on teach mode, run the job from the pendant, it records the trajectory, puts it in a database, and all he's doing is running those paths from this control system. Okay, so can't see the date, but 2021. We're there, we did it. We've automated everything, right? So let me pause it so I can explain a little bit here. I don't want to bore everybody, just in case you know about the oil industry. I'm going to explain it like you don't. So we've got a lot of our legacy equipment. This piece of equipment right here, that's an elevator. It picks up the heavy stuff. So the robots don't pick up the heavy stuff, right? They do the jobs that a human would do. So this is going to be picking up the pipe. You'll see that in a second. This our ancillary robot. It does things like doping and mud containment, and it has the tool changer on it. And this is our lower tailing robot. And these are our two operators. So you'll see this guy right here. He's driving the roughneck, and all that does is it comes in. It's a purpose-built tool. It comes in and torques up pipe. It's like a big pipe wrench. And basically, what you'll see with this guy, he's not tele-operating the robot. He's using our sequencer, and he's just pressing confirm. So let me press play, and I'll try to explain how things are going. And everything's sort of sequenced, but happening in parallel and off the critical path. So you see the elevators going up to the top. You're going to see another robot there. The ancillary robot's going in and doping, so that's off the critical path. As soon as the elevator gets up to the height, the upper robot's going to put it in the elevator. Again, you can see the operator's not doing a lot. He's just confirming and pressing things. Again, I'm sure some of the vision technology could help us advance this more. We have some unique challenges there with the sun and the environment. So anyways, we've got this guy coming in. He's going to put the stabbing guide on. And what that does is it's sort of like a cup shape. And when you put the top part of the pipe in there, it sort of guides it in. And you'll see, so the lower one's tailing it over. He's just moving it, he's pushing it. And then it's going to stab in. Did I just pause it? Uh-oh. And so you can see it's sort of guiding it in that stabbing guide. And then every robot's just going to go home and then carry on with the process. And again, the operators look really happy. They're sitting in the air conditioning. This is Texas, by the way. They don't want to be outside. Okay, so what does that mean? Did we just design this for our solution? Did we just say, okay, focus on this rig, get this done? We didn't, right? Everything is modular. The end effectors, software modules, and ROS, the software modules at the top layer. We've broken it up to where you could take, all the different pieces and look at what your application is and go, I want this, configure some stuff in the RDFs, in the launch files, and you're good to go. It also gives us room to grow, right? Because what I showed you guys is not even the tip of the iceberg. So what are we doing? As I said, it's scalable. The framework for all the path planning and collision avoidance is NOV ROS. Basically, we refer ROS as it's the access controller and collision avoidance, right? It does our path planning. We don't rely on it for any top layer user interfaces. We do that ourselves. So basically, I kind of mentioned it. What we're missing here is the robots can't make any adjustments by themselves, right? So if that pipe's a little bit off, you have to stop and a guy has to go out there and tail that one pipe in. So we are right now looking at vision systems. We're leveraging ROS. We're using 2D cameras and edge machines. So we are doing a lot of that now. Again, our biggest challenge is our environment. I saw a lot of cool stuff at Automate and I said, that's great. Can I get a couple of those? He's like, yeah, sure. Tell me about your application. Oh, it's outside. He's like, let me just stop you right there. It won't work. Right. So we've got a lot of that it won't work stuff. But again, we're pushing through it. Basically, we've launched this product since 2 years ago. We've launched, right? We've got customers, we're productizing, we're manufacturing. So it's out there. And that's kind of the end. This is our marketing video. My contact information there if you want to buy anything. I'm kidding. I'm not a salesman. Questions? Anything? Okay. I don't know. Okay, you're the pointer. I'll let you decide. Okay. So it is our product robots are RTX 215, RTX 250, and they're originally blue, and we have them painted red. So yes, they are GPs. But
As part of that question, I saw it was on Access. Did you use
so the guy that could tell you what IK solver we used isn't here. I don't know how to answer that, but yes, we use Movement, right? And we also use ROS-I, and the name of the version of ROS that we're using was on one of the gravestones earlier. So anyone that wants to talk about a transition plan, but again, we're launching, right? So it's a risk to just go, hey, let's jump onto that ship, but we do need to do it.
Why didn't reference?
So when you said that approach managers say, oh, our application's outdoors and they stop there. I noticed your robot did have like with the shoulder, not so on the wrist. Does it tolerate better?
Well, we don't make robots, but yes, so far the robots, yeah.
That's 5 and 6 axes.
Correct.
So, yeah, for those online, Roger Christian Scott was adding some detail about IP67 ratings out from 4 through 6, correct?
Right.
And so in this particular application that you saw, in order for us to, again, be agile and do things rapidly, let me back up. We partnered with Yaskawa to make a robot that they could sort of do some slight modifications that work for our application, because it's not just sun and dirt and things like that. That drill floor has hazardous gases, right? Picture it almost like a paint booth, right? It's got explosive gases, so we need to manage that. In this particular application, we're purging that jacket, so you see it's covering all the motors and things like that. Our product version, we don't need to purge. We use the jacket just for added protection, but it's not required.
And you know, format. So I think the functions that we saw seem like it's just the scale control.
Correct.
Was it the coordinated motion, the top robot, the bottom robot? Just getting everything working together in a sequence that had a human machine interface for the guy in the control team. So, what challenge did ROS solve that this guy was controlling?
Okay, so I didn't highlight as much as I did last time, but when we first started, my boss was like, hey, you need to go to San Antonio, you need to learn ROS. And I'm like, what's ROS? I have no idea, right? So there were reasons for that, and hopefully Roger doesn't get mad at me, but let's say if Roger does get mad at me someday and he won't sell me robots anymore. We need the ability as a large organization to go, okay, hey, we've built this technology stack. Now we have to change this thing down here. We don't have to redo everything. That was the first thing. But, and to answer the other part of that question, there's no coordinated motion happening, but there is some advantages that I think ROS gives us as far as like collision avoidance and things like that. Is that sort of?
So you're using collision avoidance?
We are, yeah. So, okay, we're using collision avoidance and path planning where everything's pre-planned offline and put to a database. What we found was a lot of our constraints in our path planning, it took too long to plan on the fly, right, with the hardware we're using. So I think a lot of people are used to big servers, really awesome machines where you can compile in like 2 seconds. Our IPCs took like 20 minutes to compile our code and probably longer sometimes to execute some of our trajectories. So everything you saw was more or less on the fly, except for our linear interpolated moves, so the straight movements basically. Again, we're looking at more better, that's not a word, like some of the NVIDIA edge machines to maybe improve some of that, with the GPUs and some of that path planning on the fly.
We'll get a question. Do you make a question from the
At which, like, probably type. So let me try to explain from the bottom to the top, because it's a technology stack, right? And like I said, we're multidisciplined. So in order to do that, it was a software, electrical, and mechanical effort. So I'll start at the bottom. Basically, if you look at like the RViz move it level, it's using that collision stuff right there. So it thinks it has this tool, right? And you don't want it to run into other robots or structure, right? And the twist claw is much smaller than the mud bucket. So ROS needs to know that those things change out. So we use dynamic collision objects. And I don't know if you guys already figured that out, but we wrote all that stuff ourselves. So we're swapping out end effectors. We're actually dynamically changing pipe in the scene. So we started out with everything static, but now we can, when the pipe moves, it's purple, and you can see the purple thing moving, things like that. So we had to figure out how to make that work for collision, but then also it kind of matters when you take a next step up, right? So you've got your higher level control system. That's where you're telling it to change, right? You're like, okay, go be a mud bucket. But then you got to be able to control the mud bucket, and you got to be able to turn the dope on and off. So that happens at the higher level. So it needs to know that it was changed out at the lower level. And then there's also sensors, electrical, that you're coming out of the rack and it's locked. Did I answer the question? Okay. So just designing it mechanically was fun. Yes. It's passed. Well, yes. So we use it's like I kind of mentioned it. We said, okay, look, we could run stuff through the robot and okay, let's run some airlines. Great. Now we can use one of those off the shelf tool changers. Where does it stop? How many hoses are we going to run through the robot before we go, okay, we got 50 hoses. Now, its capacity is less. So we said, look, nothing through the robot. So we put a lot of people on figuring out how to put it in a rack and use the robot to disconnect it.
We probably have one more.
Yeah, my question was, with this system, it's awesome, by the way. How much is it for retrofitting like existing setups to replace the humans, and how much of it is it new drill sites with new capital investments?
That's a really great question, and I hope our customers see this. As well as being agnostic and scalable, we looked at where the market was, and nobody has any money right now. Nobody's building rigs, right? So if we have a value proposition to them and say, you can reduce personnel, we better be able to do that on the rigs that they have. So everything is self-contained. If you have space, we can fit it. That's the whole idea, is we don't want you to build another rig. We want you to put this on the ones you have.
All right, we're gonna start. Justin, thank you.